This is Mr. Holsey with H Squared Sufficiently Understood Science, and today we're going to be talking about plate boundaries. Before we get into a proper discussion of the different plate boundaries and their different effects, it's important to understand the different layers of the Earth. Now, the uppermost part of the mantle and crust are known as the lithosphere. This is the area that we live on. And so this is where these fault lines are going to occur and where the plates of our planet sit on top of the mantle. So the mantle is broken into two parts, the asthenosphere and the mesosphere, excuse me. The asthenosphere is actually less dense than the mesosphere, meaning it's more malleable and moves a bit more. The mesosphere is more of a solid. Now, keep in mind, this is all based on theory. We've never been that deep down in the crust. I think the furthest we've ever drilled is about 12 miles. So we've never even made it to the mantle. But we can assume that the interior of the mantle, as you go down, becomes more and more dense due to gravitational forces, which may cause some confusion when you're thinking of how convection currents can affect the plate movements. But keep in mind that this is moving over millions of years in order to create any noticeable change. Now, the mantle is going to go down about 2,900 kilometers before we reach the outer core. Now here it's going to be liquid. We believe it's a liquid outer core, and it ranges from 2,900 kilometers all the way to 5,155 kilometers. Following this, we have the solid inner core, which goes from 5,155 kilometers all the way down to 6,371 kilometers. We believe that this is a solid as well, and is made of mostly iron and nickel. The reason we believe that it is almost entirely solid at the inner core is the way that waves move through our planet. As they go through these layers, they get bent. And so this gives us an idea of the composition of these layers and their density. So once again, going from the inside out, the inner core is composed of mostly solid iron and nickel, whereas the outer core is composed mostly of liquid iron and nickel. The mantle being composed of molten rock that moves through the process of convection. The asthenosphere is made of mantle rock that flows slowly, allowing tectonic plates to move on top of it, and the lithosphere is the cool outermost layer of the Earth. In other words, our crust. Now, once again, it is believed that tectonic plates are moved by several different forces. The rotation of the Earth, tidal forces of the sun and moon, gravitational pull, and convection cells. And so this convection cell is going to be very important in determining what kind of plate boundaries we're going to be dealing with. So as it moves, these convection currents, I'm going to redo that, rise and fall, and rise and fall. And these little cells are going to drag these plates along with them. So hotter mantle material will rise upward, and cooler mantle material will fall down or subduct. Now there are three types of plate boundaries. each related to the movement seen along that boundaries. We have divergent boundaries where the plates move away from one another. We can see that indicated by the arrows right here. They move away, they diverge. We have convergent boundaries where the plates move towards one another. And we have transform boundaries where the plates slide past one another. And we're going to discuss what each three of these types of boundaries really entail. So we're going to start off with divergent boundaries. Now, this is a linear feature that exists between two tectonic plates that are moving away from each other. These areas can form in the middle of continents or on the ocean floor. Now, as these plates pull apart, hot molten material can rise up this newly formed pathway to the surface, causing volcanic activity. And we can see that as these plates are moving apart, we see the hot molten material rise up to fill in the gap. But also, as these divergent boundaries eventually meet convergent boundaries, we'll also see volcanic activity. So as these things pull apart, the plates are pulling apart on the ocean floor, oceanic plates, whenever they move away from each other, they create mid-ocean ridges where molten material is rising up to fill in the space that was left behind. And as these plates move apart, that molten material creates these ridges. And so we call these ocean ridges. Rift valleys are formed where two continental plates move away from one another. And so this is where you have a divergent boundary occurring on a continent. So over time, as these pull apart from one another, the interior is going to start falling down, creating these valleys. One of the most notable examples of this is in Africa, in the Great Rift Valley, the African Rift Valley. So essentially, the presence of this convection cell causes the plates to break apart and act also as a source of new molten material. So this is called continental rifting right here, and can actually cause continents to break apart. So this map shows the age of the oceanic crust. The red coloring shows the youngest ages, while the dark blue shows the oldest ages, which can range up to 200 million years old. So if we look at this, we can try to figure out where divergent boundaries and ridges are located. Because where these plates are Divergent boundaries are where plates are pulling apart and new material is being produced. The ocean ridges are in the middle of the red areas. The boundaries are in fact shown on this map. And we can see the progression of oceanic crust getting older away from the oceanic ridges, almost like a conveyor belt. Now, not only do we see these in the ocean, but we see them on land features, such as right here. This is Iceland, where we see a divergent boundary running straight through land. So Iceland is located right on top of a divergent boundary. In fact, the island exists because of this feature. As the North American and Eurasian plates are pulled apart, and you can see the Eurasian plate right here and the North American plate right there, volcanic activity is occurring along the cracks. And so with cracks and fissures, and we can see that in the video, just how much volcanic activity is occurring. So with many eruptions over time, the island grew out of the sea. Now, why don't we have islands like Iceland wherever we get an ocean ridge? Now, the reason is scientists believe that there's a large mantle plume, basically an upwelling of hot mantle material located right underneath where Iceland has formed. This would mean that more material, would be erupted in the Iceland area compared with if there was just a divergent boundary without the plume underneath it. And so Iceland has a little extra amount of molten material that allows it to have these very specific features and more molten material rising throughout its formation. Transform boundaries are areas where plates slide past each other. The San Andreas Fault, which we can see a view of the San Andreas Fault right there, is adjacent to the city of San Francisco and is a great example of a transform boundary between the Pacific Plate and the North American Plate. Essentially, this is where you're going to find the strongest earthquakes because there is a lot of energy, frictional forces that build up between these types of boundaries. An easy experiment you can do at home is to take your fist, put them in balls, and interlock your knuckles. Push your hands together rather tightly and then try to slide them past one another. You'll feel the friction build up and then pop as it goes loose. And that's like an earthquake, releasing all that built up energy. Here we can see an example of a strike-slip fault, and it can cause rivers to change location and cause movement. This change in the Earth's surface is a term we call deformation, or deformity is changing something. And so it will actually move the Earth's surface quite a bit and very noticeably, but since it's moving side to side. Now, convergent boundaries are where plates move toward one another. There are three types of convergent boundaries, each defined by what type of crust, either continental or oceanic, is coming together. Therefore, we can have continental to continental collisions, continental to oceanic crust collisions, or ocean to ocean collisions. And these are going to form different types of land masses as they combine. So when continental crust pushes against continental crust, both sides of the convergent boundary have the same properties. Think back to the description of continental crust as basically thick and buoyant. Neither side of the boundary wants to sink beneath the other side, and as a result, the two plates push against each other and the crust buckles and cracks, pushing up and down into the mantle. High mountain ranges are going to be formed using this. For example, the European Alps and Himalayas formed in this way. And so they're pushing against each other, kind of like if you were to push the tips of your fingers together. It rises up. Here's a little animation showing how the Himalayas were formed. You can see the Indian subcontinent slamming into Asia. Prior, it was oceanic crust being pushed under, but as the more buoyant continental crust met the continental crust of Asia, it began pushing it up. Now, the Himalayan mountains are constantly growing, and as India is pushed further and further into the Asian crust, Asian plate, it will continue to grow. Now, at a convergent boundary where continental crust pushes against oceanic crust, the oceanic crust, which is thinner and more dense than the continental crust, actually sinks below that continental crust. And this is what we call a subduction zone. So the oceanic crust descends into the mantle at a rate of only centimeters per year. And this oceanic crust is called the subducting slab. And we can see that right here. So when the subducting slab actually reaches a depth of around 100 kilometers, it begins to dehydrate and release water into the overlying mantle wedge, which goes over it. And in addition, the addition of this water, into the mantle wedge changes its melting point of the molten material, thereby forming new melt, which will begin to rise. Now, as it rises, this less dense material will eventually make its way up to the surface and form volcanoes. And so it feeds the magma into the volcano. And we can also see another formation we'll talk about. This is called a trench. And we'll take a closer look at those in just a minute. This is where we see these formed at subduction zones, where plates are being pushed down. So subduction is a way of recycling the oceanic crust. Eventually, the subducting slab sinks down into the mantle to be recycled, and is for this reason that the oceanic crust is much younger than the continental crust, which is not recycled. So we're going to take a look at this in action. There we have the more dense oceanic crust being pushed down. We can see the trench right there where they connect. Now, as it reaches down, it dehydrates and causes the melting temperature to change. And that less dense material is then going to rise, forming new land masses in the form of volcanic activity. So another feature of those subduction zones, as we mentioned earlier, is the formation of trenches. And these are formed where subduction occurs. We can also find very powerful earthquakes from these. The 2004 tsunami, Indian Ocean tsunami, was caused from materials from an earthquake that occurred along a trench. So trenches form where the subduction occurs. Basically, it can be it's pushing that denser material down underneath the more buoyant material. And so here we can see the different types of plate boundaries on our planet. You can see in red triangles, we have convergent zones where the plates are coming together. And it's quite interesting to look at because if you are kind of following along, like especially like here in South America, along these convergent boundaries, we see large mountains forming. Right here, where the Himalayas are, we see large mountains, and these form different mountain ranges. Then we have the divergent boundaries in this blue, where we see a lot of seafloor spreading occurring. Then we have transform faults, which are kind of this straighter line. But we can also see the direction of plate motion. And so we see arrows going in this direction, in this direction. We can see how they're diverging and converging. So if we have arrows going in this direction and an arrow going in this direction, we can see how they would converge. Well, that does it for today. This has been Mr. Holsey of A Squared Sufficiently Understood Science. I hope you enjoyed our tutorial on plate boundaries. Remember to hit the like, share, and subscribe button, and click the bell notification to know when we post new tutorials. All right, see you next time.